All right, this is going to be a problem review of 2B11. 2B11 is a cone and plate viscometer, and you can read all of this, but basically for part A, the goal is to find the velocity in the phi direction, which is, so this plate viscometer, it's basically just like, it looks like this, but it's like a circle, and it's going to rotate in like this direction. Due to the change, or due to fluid viscosity, or as a function of fluid viscosity. So basically we're just trying to find that rotation, and that will be this function here. So basically you need to kind of just understand what's going on, like with the system itself. All right, this symbol is omega, so in radians per second. So if velocity is meters per second and radius is length per radians, omega is radians per second and radius is length per radian, and that's because the circumference of a circle is 2 pi times the radius. So if you're thinking about the radius, there'll be one radius for every 2 pi, and there's 2 pi in there's 2 pi radians in a single revolution. So radius, the units of radius is length per radian, and the units of omega is radians per second. So the radians and the top and the numerator and denominator of the denominator of the radius and the numerator of omega will cancel out, and you'll be left with length per second, which is meters per second, which is velocity. So that's where this formula comes from. I should have written those units out, but I didn't when I was doing this. So yeah, basically you gotta like look at the figure and just like kind of figure out like what the heck is even going on. So what this description is trying to say, okay, so yeah, what this part is saying, assume the local velocity distribution in the gap can be very closely approximated. That basically is saying that the angle that theta makes here is basically just a straight line. So when we go back to my rendition of the drawing, this is basically a straight line. So the top plate is moving and the bottom plate is stationary. So at a point theta here, where it's at the top plate, it'll be V max, and at the bottom plate, it'll be V0. So, and the relationship between theta and these velocities is going to be linear, because we're basically saying that this like line or like line segment of theta here is completely straight, or we're approximating it straight. So that's why we can make a linear relationship between theta and velocity. And so the range of theta, so if you go back to the earlier drawing, theta originates from the top of the rotation thing. So this will be theta equals 0 up top, and this will be at the bottom, it'll be theta equals pi over 2, and that's because a quarter turn of a circle is pi over 2 radians, because there's 2 pi radians in a full rotation of a circle. So if this distance here is this trident thing, this trident thing is in the drawing, that distance is, we're calling that the trident. So yeah, that distance is trident. So theta is from pi minus that trident. Again, that's, or pi over 2 minus that trident. And that's because this distance here all the way to this non-moving surface, this is pi over 2. And this height here is trident radians. And so this height here is pi over 2 minus the trident radians. And then obviously the pi over 2 is just this length here. Yeah. yeah, so because the trident is so small, the small line segment portion of theta within this velocity profile zone can be approximated as completely vertical. So yeah, that's just, again, saying that because this is completely vertical, it'll have a linear relationship with this velocity profile here. And this means that you can use it to measure the magnitude of velocity at position theta within the bounds. And basically, I just, for this equation, from like knowing all this and like drawing this, I kind of just made this equation. And obviously, there's no work, but you can kind of just like intuit what the equation is going to be. And you can double check that by checking the boundary conditions. So v theta divided by r is going to be equal to um, sigma, or yeah, sigma at this point here, which is theta minus the trident, or pi over 2 minus the trident. Sorry, um, 0, and that's because pi over 2 minus, obviously we're inserting this theta here, pi over 2 minus pi over 2 minus the trident, and then you divide the trident, and that's just going to be 1, and then you're left with theta. And then we're going to check the other boundary condition, which is at pi over 2, which is its bottom thing here, and that's theta of pi over 2. So you just get pi over 2 minus pi over 2, and so the v theta, or v phi divided by r equals 0. Okay, so now part B. B from this velocity distribution and equation, this in appendix B1, show that the reasonable expression for shear stress is this equation. So basically, we're just going to need to find the generic expression for this equation, and that's going to be in the appendix. So I'll go there now. It's spherical coordinates, sorry. B.1-19. So that's where you get that equation from, and I'll go back now. Yeah, so dv theta d phi equals 0, and that's because the system is symmetrical in the phi direction, and the phi direction is just this direction around the circle. So obviously the velocities are just going to be like the same around the radius for these circles. So it's not like, So the velocities are different, like up and down, but they're not different due to phi, and they are going to be different due to r, but the radius. But that's not really the problem that we're like going through. So yeah, that's why this goes to 0, and the rest of this is still correct. So yeah, this velocity direction is actually like going around with the circle because the circle is rotating. So like the velocities are like in the direction of the rotation. So the velocities aren't actually outwards. So it is v phi. It's not v theta. So this is theta. This is theta, but this is phi. This is phi, and this is theta. This is theta. Sorry, this is kind of confusing how it's written. I guess I'll just try to edit it around. But yeah. So yeah, this expression goes to 0, and we have the equation for this expression. And we're going to derive it, take it as a derivative with respect to theta. So yeah, we simplify the expression. Use our theta. and sine pi over 2 is basically sine pi over 2 is basically 1. Yeah, sine pi over 2 is basically 1, and so sine pi over 2 is basically 1, and since the trident is basically like a really small value, it's basically just going to be 1 the whole time, so we can just cancel this out, and we can also cancel this out because this is also just going to be basically 1. Well, I guess we can just cancal them out because they're in the numerator and denominator as well, but I don't know. It's either way. They'd cancel out either way, so yeah. And so since this is a linear relationship, we can just calculate the derivative using the final initial values that we plug in to this equation with respect to theta. And these are theta, these are theta, and this is phi. So yeah, a derivative is just the final value minus the initial value divided by the final position minus the initial position. So we're just plugging in those values. And so the final value is at theta equals pi, and the initial value is at theta equals pi minus trident. And again, this is sigma r because this equation. Oh wait, yeah. So because this equation is v phi divided by r, so so if you isolate v phi, it's just sigma times r. So that's why it's sigma times r and not just sigma. And yeah, pi over 2, that's a final value, minus pi over 2 minus trident. That's the initial value. And we're canceling terms. And doing some algebra, and we get the shear stress phi sigma whatever phi theta equals mu sigma divided by trident, and that's the answer for part. That's the answer for part B. All right, now for part C. Show the torque required to turn the cone is given by this formula. The standard formula for calculating viscosity, measurements of torque, and angular velocity for a cone plate assembly with known R and trident. All right, so basically, I just looked in the book for like mentions of torque, and I found this. So this is an example with a sphere. So this is saying to evaluate the torque, you need to maintain the rotation of the sphere. We will be this will be the integral over the sphere surface of the tangential force, which is in our case it's tau theta phi, and still evaluated at r equals big R because it's the end of the that's like at the surface. So obviously the force is going to be applied at the surface of the object, or in our case it's going to be at the sphere. It's going to be at the edge of the sphere. The force is going to be applied at the edge of the sphere. So yeah, it gives you this, and this whole thing is this is the differential area for a sphere. So this will not be the same in our problem because we're using just basically a plate, or just a two-dimensional circle basically for the top plate of the system, and it's exerted on the fluid by a solid surface element multiplied by the lever arm r sine theta. And that lever arm, if you look at this, the rotation in the sphere is about, or it's about the z-axis, and it's in the y-x plane. So if we look, r sine theta, if we look at this drawing here, r sine theta is it's this line here, and that's the line that's in the y-x plane. So in our case, we could say it's r sine theta, or we can just say it's since we're just going to be like in this plane here, we can just say it's r, and that's because sine pi over 2 is basically just 1. So we could just say it's the moment arm is just r, and also because it's over us, it's over just a circle, so like it's not going to be a sphere. So basically, our moment arm is little r. It's not r sine theta because we're using just a flat surface and not a sphere. So that's what I did here. Tau z equals the integral of this force, this what is it? Shear stress force times the lever arm, which is r, or r sine theta. You could do either one, but it really is like actually r in this case because it's a planar circle, because that's the surface of the viscometer. Like if we're looking at the viscometer, that's the surface that you see. The differential area, well, I guess it gives you the differential area here too, r dr d theta, or d phi, which actually I use a different differential area just because I don't really like having to integrate twice. So I just derive a differential area here. So yeah, this is the surface and this is a differential area. So you go to here, that's radius of r, and then you go to here, this is radius of r plus delta r, to find the area of the differential area. It's just this large circle, but excluding this interior circle. So it's just area of a circle pi r squared. You're just doing the larger circle minus the smaller circle in the middle, basically. So you get this. And this delta r squared is gets canceled out, and that's because delta r itself is an infinitely small value, because that's how integration works. It's basically calculating the area under the curve, and that's over like infinitely small values. So yeah, delta r is an infinitely small value. And because of that, if you square an infinitely small decimal, it's going to be like really, really small. So like you square 10 to the negative 9, that's 10 to the negative 18. 10 to the negative 18 is like a gajillion times smaller than 10 to the negative 9. So that's why that cancels. And then obviously r squared cancels with negative r squared. So you're just left with dA equals 2 pi r delta r, or 2 pi r dr. Delta r and dr, same thing. So now we're going to insert the definition for the shear stress that we got earlier. This definition here. And just do the integral. It's pretty simple from there. And I'm taking all the stuff that basically just doesn't have to do with r. So I'm basically just taking out everything that's not r squared, I think. Yeah, 2 pi. Yeah, just taking out everything that's not r squared. R and r squared. Yeah. So yeah, integral of r squared is just r cubed divided by 3. And we're integrating over the bounds, obviously 0 to r. Those are just the radius bounds of the circle. So that's pretty self-explanatory. So yeah, the shear stress, or the torque is 2 pi viscosity, whatever this expression. And that's it for part. That's it for part C. All right, so for 2B11, turns out there is a part D, which is basically just an application of this formula here. Yeah, so it gives you a radius of 10 centimeters. Radius of 10 centimeters, which would be the radius, obviously. Gives you angle trident of 0.5 degrees, and you're going to want to convert that to radians. So I convert, 0.5 degrees equals 0.5 divided by 360. So that's like the percentage of the total circle is 0.5 divided by 360 degrees. And there's 2 pi radians in a circle. So it's basically 2 pi over 720 or pi over 360. And by the way, I'm just, the way I usually do formulas like this is I usually just convert all of the given values into SI units, and then I'll convert that SI output. So in this case, tau, or it's a torque, so it's just going to be a force times a distance, because that's the SI unit for torque. So I just convert all these individual values into SI, and then I can just know that the output is going to be also in SI units, and then I'll just convert that output, whatever unit it wants me to use. In this case, it's dyne times centimeter. All right, so continuing on, we did the angle, trident, torque dyne per centimeter, and then to turn the cone at an angle of velocity, 10 radians per minute. So radians per minute, the SI unit for that is going to be radians per second, not per minute. So you're just going to have to divide that by 60. So it's going to be like 0.6. I think that's what I did. Yeah, I kind of forgot until like I was actually getting the formula. So yeah, 10 divided by 60 is 0.6. And then centipoise, you can just look at like what the prefix is for like this poise. The C is for whatever that prefix is. They're common among all SI units. So yeah, centimeter, centipoise. A centi is like 100. There's 100 in the base unit. So 100 centipoise equals 1 poise, like 100 centimeters equals 1 meter. And 1 poise equals 0.1 Pascal second, which is the SI unit for pressure. SI unit for pressure is Pascal times second. And I just looked this conversion up on the internet. It's pretty readily available. Yeah, so that's all the units I needed to get into SI. And 1 Newton meter, well, there's 100,000 dyne in a Newton, and there's 100 centimeters in a meter. So converting between those, you just multiply these together, and you get 1 Newton meter equals 10 million dyne centimeters. So when I did this, this is what the SI units here. All the SI units are plugged in. I get 0.004, and then I just multiply that by 10 million, and I get 40,000 right here. So yeah, that's it for the problem. If you have any questions about this problem, any other problem that you would like to have solved, or just anything you would think I should be doing better in this channel, feel free to comment. If you want to say anything else, also feel free to comment. Why not? Have a good day. Bye-bye.